so please don't.
Yes.
Oh well.
And I can't put it up.
It's
Then I
safe
have
as
to-
long as the student says
Then I have to
it.
go home and then like re-record it. So anyways. Alright, Newton's first law of motion. You are welcome to remember verbatim truly what Newton's first law is. An object in motion stays in motion, object stays at rest. But people really don't quite understand the implications of when you say that. So before we get there with Newton's first law of motion, I do want a little bit of a history lesson about where force is and the idea of forces came from. So the first written idea of forces was Aristotle. Wicked smart dude. But science wasn't very developed back in his day, like 350 BC, so like 2,400 years ago almost at this point. Instead, when they came to science, they just philosophically thought about it, and he wasn't too far off. So he had this idea of the concept of the mover. And so if a force is applied to something, if a push is applied, there's a reaction to it. Fast forward a couple hundred years, we got Sir Isaac Newton. He's Sir, so he was knighted by the Queen or King, I forget at this point. All right. Dude was stupid weird though. All right. At one point, we believed light came from our eyes, and that's why we could see stuff. So to prove people wrong, he shoved a needle in his eye, and then he couldn't see anything. All right. And he's like, I can't see anything. Dude was weird. All right.
Wait, what?
He's also a terrible note taker. So when we try to read his lab notes from back in his day, people really can't understand what he's going on. He was just an odd duck. All right, now I'm going to tweak this word though. He's pretty much invented calculus. That's wrong. He discovered it. You can't really invent math. But anyways, so if you're ever doing calculus and you want to shake your hand at, I don't know, whoever, the reason you're studying calculus, you can blame Isaac Newton. The reason being is that when you look at the physical world, Sir Isaac Newton had the projectile formulas, the kinematic equations. He had those. But then he found out they don't actually, they're not perfect. There's a wide margin of error when you look at really small objects versus really big objects like planets. And so then he discovered, I would say, the first steps of planetary motion. And so he used calculus to describe that. And then he found out that calculus to describe planetary motion actually works with motion on Earth. Dude was weird. What did he get to eventually? Got to this. So this is like the bread and butter of this whole lesson, okay? If there's anything I'd write down verbatim, it would be this, and I'm going to be here for a little while, okay? While you're getting that, I'm going to go do attendance, see who's here, who's not here. Take my public board. I blame justice. I do want to make sure you denote it. This little symbol here means does not equal. Make sure that little slash is in there. You can write it like that, or you can literally write out does not equal. It's up to you. All right. Does everybody know we have e-learning day on Friday? Okay. My e-learning assignment is a reading. You're welcome to do that early. It is currently up. It's like you read an article, a couple paragraphs, type it out. Done.
Do we have a test or a quiz on?
We'll do a quiz on Thursday. But this unit's pretty simple. Straightforward.
What is F subscript of net?
Net force.
I'll get there.
Isn't it?
I'll get there. I just want you, instead of while writing and listening to me, I want to give you a head start. Evan, how's your grip strength?
Pretty good.
Cool. All right. At a certain point, I'm going to trust you with this.
Okay.
All right. I am pulling on this meter stick, and Evan is also pulling back. Now, the harder I pull, the harder he's going to pull. Would you agree for the most part we're not moving?
Yeah.
All right. For the most part, there's no motion. So what can describe it as errors. All the forces of me pulling on you and you pulling back are going to be balanced. The net forces, or the sum of all the forces of the situation, equals 0. Okay? Now, when I'm seriously hold, okay? Now, pull back and hit jacket. Alright? Now, the harder I pull is the harder he pulls. Doesn't matter how big the force is. Legitimately, if he lets go, I'm falling off. Okay? No matter how big the forces are, as long as they're in balance, okay, there's going to be no motion. So when you look at forces, they could be 3 newtons, they could be 300 newtons. As long as, thank you. I'm getting a little concerned there.
My hands are
Okay.
very.
Alright. If the forces of all the summation of the forces added up equals 0, one of 2 instances are always going to be true. The first one is that we just talked about no motion. We did not move. Okay, now let's talk about the other one. This other one likes to get people tripped up for a little bit. Okay? Let's try it out. Avery and Hannah, can I use you for the example?
Sure.
It's an allegorical example. We're just
Yeah.
going to talk about it. But I need one person to be the bad character and one person to be the good character.
See who he puts,
Do you want me to pick or do you want to pick?
Let's leave it to you.
Okay. All right. So, Hannah and Avery are fighting on the International Space Station. Okay. They're in outer space. There's no gravity pulling on them. All right. It's the end of some action movie. All right. Hannah, being the evil character, all right, gets Spartan kicked off of the edge of the International Space Station, and she goes flying away. Let's give you some hair. I don't know why you have hair in the International Space Station. Should be a national outfit, but okay. Hannah goes flying away forever. Let's say she's going at a velocity of, let's say, 5 meters per second. There's no gravity in outer space. Since there's no gravity in outer space, there are no forces acting on her. She's going to go 5 meters per second for forever. There's nothing to slow her down. Okay. The chance of you getting kicked off the International Space Station and hitting the next planet, you'll be long dead before then.
How am I the bad guy if Avery kicked me off of the space station?
Because it's the climax of the action movie.
It's like Darth Vader and
Maybe like
Luke
you were killing
Skywalker.
people. I was like, no. So I was
Spartan.
Yeah, you're killing people, Hannah, so I'll kill you.
No, I don't know. I'm trying to think of
Okay.
a movie. I'm just saying.
Skywalker, Nobi, Kenobi.
Okay.
You're out of this.
So here's what I want to say. One of 2 instances are true. If all the forces added up equal 0, one of 2 instances are true. Either going to go constant velocity, think about Hannah floating away, 5 meters a second, or no motion. It's not going to move at all. What if forces are unbalanced? Well, then you're just going to accelerate in the direction of the larger force. Okay? So if I were to, going back here. All right, hold both hands. You ready?
Yep.
You sure?
Yeah.
Positive.
Yes.
Sure?
I'm really good.
Ready?
Here I go.
All right, if I pull with more than what Evan's ready to pull back with, he's going to accelerate in the direction of me. Okay?
Well, you had the advantage. You're standing up.
Sure. I always have the advantage. Kidding me? I have the high ground here. There's your Star Wars reference.
Okay, Obi-Wan.
Okay. So looking at the first picture, we got 300 newtons left, 300 newtons right. They balance out, cancel out, no motion. However, in tug of war, once one side starts to pull with more force than the other, everybody will accelerate in that direction. Thought about inserting a Squid Game reference.
You should.
I watched it over break and I was like, this has too much hype. It's not worth
I
it.
can't have
So
the
did
other
Miss
sibling.
Too much
You was
hype.
so
Is that
Too
what
much
you're
hype.
saying?
Not worth it.
You
I
don't
don't
think
think
it's
it's
good?
good.
I
I think
watched
it's
it
good,
yet.
but
Okay. Since forces are vectors, if they're going the same direction, you add them. That makes sense. If me and another person were going to push on the same side of something in the same direction, you will add our forces together. If they're in different directions, you subtract them. Makes sense. But every once in a while they're going to pop up. We're going to see angles. Whenever you see an angle in this class, you automatically think trig function, sine, cosine, tangent. Cool. We good here? Can I move on? Ah, hold on.
I'm drawing Hannah real quick.
Yeah, just wait for mom, I think.
I'm holding. Get it? Hold on. At least you smile from it. Not a lot of people get my jokes. I enjoy them.
It's kind of like dad jokes.
What I really, really enjoy is when I'll say a joke and not many people get it except for one kid in the back who's just like, We're good? Okay.
Has that happened in this class yet?
Oh,
Shh. I'm skipping this because I think we have better examples here later on. Okay. But I do want to talk about some hidden forces. Forces we don't think about too much. Okay. These two hidden forces are always going to be evident. What we got to talk about? So, what prevents my body from flying away and leaving Earth permanently?
Gravity.
Well, that's gravity. Gravity's an acceleration, right?
Yeah.
But what is the actual name of the force that pulls me down?
Weight.
Weight. My weight, which we use to denote with a W, all right? We can also say force due to gravity, but for reasons I don't want to unpack right now, I use weight more often than that. Okay? What about if I were to have an infinitely long hallway or a table, and I would roll a ball down on it? Friction, right? Friction would slow you down. So we just call this F sub F for friction. Okay, so with that in mind, let's draw our very first free body diagram. So this is the other big meat and potatoes slide of the whole thing. The rest of it is just examples. Okay? When you draw a free body diagram, it's also called an FBD, we want to include a couple or whatever forces are involved. Okay? I'm going to stay there for a second. I'm going to shrink it a little bit. Maybe people can see it better. I'm also going to draw a little. You can say force due to gravity, but I really prefer weight. Technically, they're both the same, so I'm not going to argue either. All right?
Is that force of gravity or force with gravity?
Force due to gravity. That's what it's called. Which is called weight. The next force that likes to throw people for a loop. Sorry, Mary Kate. I did this earlier. I didn't die yet.
I didn't
Keywords
die
yet.
yet.
Okay. Mary Kate, am I going through this table? No. But I do have weight, right?
Yeah.
I'll say my weight's about 1,000 newtons. So if I'm pushing down on this table with 1,000 newtons, what does the table have to be pushing back with in order to make me not move? 1,000, right? So what do we call this force? Well, the force pointing upwards is called force normal. Normal is a math term, and I really don't want to unpack what normal is because it's when you usually deal with three-dimensional things. So we're just going to say upwards is F normal or perpendicular to the surface. I haven't busted a knee yet, so.
You say yes, what's going to happen?
Accidents
never
happen.
know.
Okay.
From that high up? I've seen people break their axles from that high up.
Yes.
So force normal
No, I broke my ankle from the ground.
is written as
Of course I was
upwards. If we apply a force, we just call it force applied. However, sometimes based on the situation you're in, you can call it other certain things. And you already know this word. If I were to pull on a rope, the rope is under what?
Stress.
Stress is one word, but I'm looking for the T word. Tension. So, if you're pulling on the rope, you can call it tension. There's also compression forces.
Is stress a wrong answer? Would you consider that?
Stress is more of a materials question.
Okay.
Stress load is often how much force does it take to break something.
Have you ever broke one of those?
It takes a lot more force than you think it is.
Okay.
So tension is
Tension is always a pulling force. So, hold this. If I were to pull on this meter stick, the meter stick is under tension. It's a tension force.
Yeah.
If I were to push on this meter stick, that's a compression force.
Yeah.
But both instances, that's a force applied. Over there?
Yeah.
So tension is always a pulling. It's a pulling force. Compression is pushing those molecules together. Now there's other ones like shear, but that's like a twisting force. Right, cutting through something. The last one is friction, force friction. Force and friction, which we just denote as FF.
Wait.
Weight is downwards. Oh, I got a lot of them today.
What?
You're missing the jokes me and Hannah are saying. They're pretty funny.
Wait, what's FAOT?
When you were talking about hidden
What?
forces,
Force applied tension.
she hit her hand.
I'm glad you turned a good mood today.
Force applied though.
Okay. Force applied could be tension or force due to compression forces. I'm often just going to denote it as force applied. The only reason I bring it up is that on some of your homework, I'll say the rope's under tension, and I want you to understand that's an applied force. So free body diagrams. I had a student a couple years ago also call these friggin' big dots, because in AP Physics, you often draw just a dot diagram. Alright? So free body diagrams, friggin' big dots, you call it whatever you want. I want you to draw the object with all the forces on it. Okay? Am I good to do an example now?
Yeah.
Did you draw the thing? 1 second. You probably want to draw one.
You good, Dan? You sure? I haven't seen smart ones today. Am I gonna move on?
Yeah.
You got a question, Jalen?
May I use the restroom after first example?
Sure. You just go now. I'm gonna keep talking.
Okay. I didn't know if you were gonna do an
Nope.
example now.
I'm gonna do an example, but we're gonna move on. We're not gonna wait for you. Okay. Ball sitting on a table, not moving. Here's the shot for candy now. Alright, what forces are gonna be involved? Okay, do you think you got it?
Weight
What direction is weight gonna be?
down.
Okay. What else?
Would it be friction
Ball's not moving.
of not moving? Would it be normal force too?
Normal force, absolutely. Is this ball falling through the table?
No.
No. So that means that something has to be pushing up. Okay? So we got weight, force normal. Cool. Second one, ball rolling across the table. Let's draw all the forces involved. Free body diagram, ball rolling across the table. What do you got, Sawyer?
Force of friction.
What direction is friction going to be?
Left.
The ball is going to the right, so friction is going to be left. What else is there going to be?
There's gonna be weight.
Absolutely.
And then friction. What?
Not friction normal.
Force.
Force normal, absolutely. So force normal will be upwards. Fantastic. Right? Is everybody good on those two examples? Not too bad? Okay. Ball falling down from a really tall cliff. Ball's going this way. What forces are going to be acting on the ball? I got a problem with that G word you just said. What is it, Avery?
Wait.
Weight, absolutely.
I thought you were gonna say.
Is there any other forces acting on the ball?
Are you still asking?
Mm-hmm.
Were you just like dropping it, or did you push it off?
Doesn't matter.
No.
Then yeah, because you'll have friction and applied force.
When a ball is in free fall,
Uh-uh.
is anything else touching it?
No. But if you throw it,
If I throw it,
But it just says
but it's
falling.
still falling.
Yeah.
What's normal?
I agree with you. If I were to throwing the ball off a cliff and it's still touching my hand, there would be an applied force. But I'm just talking about the ball just falling.
But even after you throw it, there's still applied force.
he's not throwing it. He's seeing it.
There's nothing touching.
I asked him
just
if he
like
was throwing it, and he
falling
said it didn't matter whether it was just dropping or if you threw it.
I think she's
Right.
overthinking this.
No.
Probably.
No.
but-
This goes back to a thing. Acceleration in the x direction is 0 once you've launched it, right?
Yeah.
Oh yeah,
Right?
but velocity.
But so the velocity in the x direction is constant. If your velocity in the x direction is constant, there's no forces in the x direction.
Okay.
Okay. That was a quick, we went way down the rabbit hole, what I was not prepared to do today. That's like later down the road. Okay. But I'm just saying, if the ball's falling, you could have launched it out of a cannon, you could have dropped it off a cliff. Doesn't matter. The only force pulling downwards on it is weight. We ignore air friction in this class, at least for right now. We might tinker around with air friction later, but to truly calculate it, you have to know calculus, so we just kind of ignore it for a lot of the time. Okay?
So is there an equation to find out air friction for a certain object? And it's a
Calculus.
I bet it's on one of these posters.
Nope.
No.
I've never taught calculus-based physics. Okay.
That's triggering though.
All right. For this first one, what can I say the net forces are? Hey, you ready? You ready for nerds?
Sure.
What do you want? You didn't seem excited about that. What are you feeling? I got Laffy Taffy in my hand now. You want pink or you want yellow?
I want pink.
Okay. Do you want to read the jokes out or do you want me to?
Yeah, read the jokes.
Okay. What did the net say when the ball swished in? What did the net say when the ball swished in?
Yeah.
Nothing but net.
That's my internet.
That's
Boo.
so weird.
That was bad.
What does a ghost call their partner?
His boo.
My boo.
You're my boo.
That
Oh,
went
sure.
so far.
Okay. Let's talk about FNet for these three instances. It's either 0 or not 0. Kate, I'm going to come back to you. Ball chilling on the table. Is it moving? So FNet is what? 0, absolutely. All the forces on it are balanced. Okay. Ball rolling across the table to the right. Friction's involved. FNet equals what? What do you think? If I roll a ball, will it roll forever? What's going to slow it down?
Wait.
You're not wrong, actually. But you're not right. Friction. Friction and weight kind of go hand in hand. They hold each other's hands.
The weight of the friction.
Okay.
Or the friction. of
So,
the weight.
if friction's slowing it down, I'm going to ask a silly question. Don't overthink it. If friction's slowing it down, is it going at constant velocity? No, right? So FNet is something else other than 0. So it's not 0. I didn't want you to overthink that.
That's all you
That was a
got.
tricky question. I worded it weird.
Not really.
I didn't want you to overthink it. Okay. You understand that though?
So that's all you wrote, just
It's not 0. We're going to find out how to calculate this not 0 part later. But we're just going to keep this for here.
Do we have to have numbers involved? I'm assuming we do.
Last one. FNet equals not 0. Because it's accelerating. It's speeding up in the negative direction.
So anything that's accelerating is not zero.
If it's accelerating, FNet
Would
is
it
not
be
0.
accelerating? Would it have to be negative 9.8?
The acceleration would be negative 9.8, yes. But your FNet would not be negative 9.8. FNet equals MA. Newton's second law, but we're still in Newton's first law. Cool. Am I gonna go on? Sure. I'm thinking L is my my pace horse.
I'm good.
I think if L is good, I think everyone else is good. Okay.
So we just have to know if the force is, if the F of net is 0 or if it's not 0.
Correct.
Okay.
And if it's not 0,
What is it?
He's about to tell us.
Okay.
if it's not 0, you subtract them. If forces go in the same direction you add, if they're different, you subtract them.
Okay.
That's it. So F net for this example down here, I guess, which I should have done. They're going opposite directions, so subtract them, right?
Yep.
So it's 100 newtons. But what direction is the greater force? To the left, so this is negative 100 newtons. Cool?
Yep.
That's it. Cool? All right, let's take this. Now let's apply it to a full-blown question. All right? We have a 25 Newton box being pulled across the table to the right at a constant speed with a force of 50 newtons. Step 1, draw your free body diagram. Then calculate what we got going on. Okay? So I'm going to give you a second. I want you to try it out. Draw your free body diagram. Try it out. See if you get the same answer as me. And then see if you can figure out what force of friction and then the force normal is going to be. All right? Try it out. See where you get. I think the majority of us already like this better than projectile motion. Well, you're weird.
Yeah, thanks.
Like for good jokes. I'm just going to hop in. We're going to do the free body diagram part, and I'll hop back out. I'll give you a second to try it out. Actually, make sure you're on the right pace. All right, who wants to help me out with the forces on the free body diagram? Shot at Candy. Jalen, what do you got?
Okay, so
What's
so
the
your
first?
force normal and force gravity have to be the same
Force due to gravity.
because it's not going up or down, so they have to be the same.
Well, we're just drawing them.
Okay.
What direction is going to be force due to gravity?
Force due to gravity is down.
Down. Force due to gravity. But I prefer to call it weight, so I'm going to put both. Okay, what's that upward force called?
Force normal.
Force normal. Are there any forces in the x direction?
Yes, it's going to the right.
It's going to the right, so what do we call that?
So we're having applied force of 50 newtons.
Applied force, 50 newtons, absolutely. Is there any forces going to the left?
No.
Whoop.
There is friction, but we
Friction.
don't know friction.
We don't know it, but it is there. We're going to find it. Cool.
And the box itself is 25 newtons.
We'll get there. All I want to do is draw the free body diagram. Make sure we're on the same part. The very first thing, it says a 25 Newton box. Well, that is your weight. So your weight is 25 newtons. All right. Once you start to piece this together, you're like, wait, that's it? I'm like, yep, that's it. Okay.
What type of bottle loves water?
So here is our key word there. Mary Kate, you want your shot? Try it out. You ready? It's not going to be, I'm not asking a math question. I'm literally just asking. If you're going at constant speed, what can I say? If you're going at constant speed, where's my clicker at? I'm buying you time. Ah, I went too far. If I'm going at constant velocity or constant speed, shh. What could I say? We just said what? F net equals what? 0. So it means all the forces, when I add them up, are going to be 0. They cancel each other out. So F net is going to equal 0. That means my forces up and down cancel each other out. My forces left and right cancel each other out. You get there now, Mary Kate? Okay. All interested in, or do you want to laugh at? Or nerds? Orange or not orange? Where did I get orange from? Yellow or pink? What's up, Avery? Hannah's question? Sure.
So, if they cancel out, I think I just have an answer, but I don't know if it's right.
It probably is right.
Then should I know?
You're welcome, Zed.
Okay, so does that mean the force of normal has to be 25, and then friction has to be 50?
That's it.
Okay.
Okay. All I'm going to do then is here's why I'm going to write it this way. It's because I'm going to, for the last example, which is the next one, I'm going to bump it up a little bit in difficulty, but I'm going to follow the same thing here. I'm going to say is my force normal, which is up, is going to equal my weight. My force up is going to equal my force down. My force left is going to equal my force right. But since we already know, chill it. All right. Since we know force applied is 50 newtons, we also know friction is going to be 50. Since weight is 25, we also know force normal is 25. That's it. Boom, done. We got one more example, we're done. So like that's, if there's no angles in the problem, that's how easy the problem can be. So Evan, what do you think the next example is going to have on there?
Angles.
Angles.
Boy, I love trig.
Am I good here? Got one last step and I'm done. One last one, we're done. You good, Ella? I gotta move on? Okay, cool. All right. Same situation. We're going to go at a constant speed or constant velocity. I do have to change one thing, though. The weight of my box, we're going to call it 30 newtons. The weight of my box is 30 newtons, not 25. Xavier, you doing all right back there, man?
Yeah.
Can you help me out with some forces on my free body diagram? Okay, let's get the easy ones out of the way.
Yeah,
First force we always want to draw is weight. The weight is 30 newtons, absolutely. Is that box falling through the floor? No. So there has to be what? There has to be a force normal upwards. Okay? It's not going to be equal max, and I'll show you why in a second, okay? But I will hopefully you agree with me. There will be a friction to the left. Follow me there? Actually, I'm gonna go back a little bit. Let's do this a little bit different color. It'll make sense why in a second. I'll say friction is to the left. Go there? Cool, that's all I need from you. Ready? Feeling something particular? I'm just gonna go for whatever I find first. Nerds. Okay. So what I got is this so far. What happens when we have a force at an angle? We're gonna do some trig karate to it and break it up into its x and y components. So here is my force. It has, oh, I'm on that green. Let's try it again. It has a force applied in the x direction and has a force applied in the y direction. Does everybody see that? The red forces are going up and down. The green are going left and right. So let's do a little bit of our trig magic. Ready for that, Evan? I'm trying to pick up the pace a little bit because I don't want to run out of time. All right. What trig function am I going to use to find f sub y? Sine. Somebody got it. So sine, what's my angle?
Wait, which one were you looking for?
Fy
Oh, f of y, okay.
equals Fy over 50 newtons. Right?
Mm-hmm.
Everybody good there?
Yep.
I'm going to try to speed up because I know announcements are going to kick on here soon. So that means F sub y equals 50 sine 30, which is 25. What's the unit for force?
Newton.
Newtons. Cosine, I'm going to use for f of x. Evan, I'm going to have you do a calculator. You got a calculator handy?
Nope. 3, 2,
I just want you to double check me when I do this.
okay, so 50 cosine 30. 30 is 43.3, yep.
Now, I know I did that fast. Is everybody okay with how fast I went through that?
Mm-hmm.
I mean, we've done trig for a while now. If you're not okay with this, just feel free to pull me off to the side. I just want to squeeze this through before we get done. So now I know force in the y direction is 25. Force in the x direction is 43.3. So I'm going to write that over here. I have like a dead spot on my screen. 25, 43.3. Is everybody good here?
Yeah.
All right. I'm going to scrunch down a little bit. Over. Since F net still 0, since we're going at constant velocity, all my force is up. Force normal plus Fy have to equal weight. My 2 forces up have to equal my 1 force down. Everybody see that? If we do, like, we're looking good. We're cooking with grease. That also means my force of friction to the left equals my force applied to the right.
So,
Shall we go there?
yep.
So now all we got to do is plug in our numbers. We have the numbers. We're just going to do algebra to figure it out. To calculate force of friction, well, force of friction equals force applied in the x direction, which is 43.3.
60. Force of net. Force normal.
I'm going to run out of space here, so I'm going to come over here with it.
It should be 60.
Force normal plus
Oh, wait, no.
Fy, which is 25, equals 30.
55.
Force normal equals 5.
Wait, what? Oh, subtraction.
Subtractor. There we go.
Because
Okay. Cool. I should a lot really quick.
I think I got it.
Here's what I have for us. There are a lot of really fun labs I would like to do with this unit. The more we understand the trig part of it, the more fun stuff we can do. One of my favorite labs we do ever is I tie a flying pig to the ceiling and use trig to find the tension in the string. Super fun, but it's like I need you to understand the trig part before we get there. Okay? One lab we're also going to do is hopefully we're going to tie each other on carts and fling each other in a circle on the gym floor. But you got to understand the math.
I like that. I like
Okay.
that a lot.
All right.
I know how I feel about that.
So I'll see you in a few minutes, folks. See you tomorrow. Your homework and your e-learning assignment is already up.